Hi, my name is Orange Schwarzkopf, and
I'm a DJ Song.
this is our four-year structure of real MVP. Our project's goal was to train a neural network to learn complex spatial patterns in structures in the cosmic microwave background called CMB. Our another goal was to make sure the model can accurately generate maps and thus learn the CMB well. We learned to calculate a matrix called the Jacobian to understand how the model is making the transformation between the maps. The cosmic microwave background is the afterglow left from the Big Bang. Analyzing this cosmological map is an easy Gaussian random field. This is the map of the universe as it's a super hot plasma before anything turned into galaxies and dust. So when the Big Bang happened, it all dispersed in those fluctuations and they would get smaller and bigger. But the waves had to get to a lot of foregrounds to reach us. So the foregrounds are the foregrounds are other things that are in the way of the microwaves from the CMB, such as the lactic dust, which are shown in this image here, and galaxies, which are stars. So this image here shows the normal CMB, and then when it reached us, I had to go through all this other stuff, and you can see there's slight distortions, some hotspots are bigger, and some it looks like a little warped. And over here, this is the cosmic infrared background, which is the CIB, which was also emitted by a bunch of stuff, and it all contaminates our map. And it's not like an easy thing to write down, so we have to use the machine learning models to learn how to predict the shape, because the equations can't write it down. We have to use a neural network, which is a machine learning model inspired by the human brain, designed to recognize patterns in data. It processes through the input layers here, and it goes through all this stuff to get to an output layer, and then the network takes raw information like pixels, and then it passes it through everything, and then after you give it validation to check if it's right, and then it works its way back through back propagation to adjust the weights on how much this one affects this one until it gets better. The neural networks do things similar to linear regression, but instead of one input and one output, you can have multiple inputs, and it's more complex than a line, and it fits very complex functions. This is the real MVP, which stands for real non-volume preserving flows. It's a machine learning model, specially designed to act like a complex cosmic map and translate step by step. It takes white noise and takes it to cosmic maps, and it learns to do the reverse while it studies the stuff. So it takes really simple white noise, which is you use white noise because it's really easy to write down an equation for and use in problems, and then it takes it to much more complex maps like the cosmic map, and can use this to interpret stuff like the mass of the neutrino and how the universe was.
So these are a couple sample maps. So on the left, we have a sample that's created by our network. And on the right, you can see a sample that was computed from a model or from a no distribution. So you can see that the shape that has a very similar texture and how you have these big splotches that are present in both, as well as some finer details. The first test we did for our model was we did a log PDF test. This helps us understand how probable a model is, or a map is, and when we are creating our maps, the model will give us a log PDF, and then later on, we can also compute it analytically. So on the right-hand side, these are the log PDFs for maps that are created by our model. And you can see how, well, it appears that there's a tight scatter. It's the correlation coefficient is only 0.8, which means that it's not as accurate. On the left side, we have the validation maps, which we use to send from our maps to the white noise. And you can see here that the correlation is actually very good. It's almost 1. And so this helps us understand how accurately our model is learning the distribution. And before we go into our next test, it's important that we understand what the Fourier transform is. So the Fourier transform allows us to pick out specific frequencies as sine waves from a curve. So you can see here, we have these individual frequencies, and when you add them together, you get this whole frequency. And In this example, you can see that this is a 2 hertz frequency, so it will appear every 2 seconds. And here is a 3 hertz frequency that will occur every 3 seconds. And when you add them up, you get this wave, which will look like the two combined. So this is a very useful tool in numerous applications, including when you're trying to isolate certain sounds in sound editing. That's a very useful tool. And here what we use it for is the power spectrum, which represents the scale of temperature changes. So for a lower L represents sort of a bigger Fourier mode, which if we go back to our maps is represented by these sort of larger blobs. So you can see that the left-hand side of the power spectrum is higher up you have these larger blobs rather than the sort of finer details that you might see if the bottom of the right side of the curve is a little bit higher up. Next, we have the Jacobian, which is the end goal of the project. And the Jacobian is made up of the partial derivatives of a function from different perspectives. What this helps us understand is how our model changes its inputs into the outputs. So when you look here at the Jacobian of our model, you can see here the input is on the x-axis and the output's on the right axis, or on the left axis, and allows us to sort of pick a coordinate and understand how much of a change that a input and output is taking at that point. And then our applications in future works. So we can for future, we want to do a little bit more analysis on the Jacobian of our model to try and understand how it's taking maps from white noise to the lane space more so that we can create better models in the future. It'll also help us understand how certain other techniques that are used in some other models, how those work, and understand how we can more effectively use those. Thank you. Questions?
So AI is in the news every day, all day now.
Yes.
Do you have a better appreciation for how it can be used effectively, its limitations?
It definitely shows some of the other uses for AI, not just in generating content, but also trying to help us understand the way certain probabilities occur and helps us understand the relationship between two things in a way that is difficult for us to write down manually, and it helps us gain this understanding better.
I mean, it's more of a specific deep learning neural network of the model. So for example, if we wanted to, we could have write down, I think this one has 24 hidden layers. So it would have somewhere around 13,000 different parameters. So it would be really hard for us to do it by hand, but AI can do it a lot faster, and it would be it's way better to use it to train it to do that. Yeah.
How do you generate what is the testing data set or the validation data set that you're comparing to? And how do you evaluate the accuracy of this one?
So as I've mentioned, we use our spectrum test. So you can see that the blue line is the theory spectrum, and this is calculated from a known distribution, and we compare this with the spectrum of our model. And this allows us to see how the model is performing. And again, that log PDF test also helps us understand if the model is.
So is this on the validation set or a separate testing set?
So this is on a separate testing set that is also used for validation. That set comes from that known distribution.
Generally, the validation and testing set should be separate. The validation set would, otherwise, if you're iteratively over the epoch, you're validating the validation set, and that's part of the training of models, then wouldn't you conflate the testing or deflate the testing perspective?
It's a separate set from our training set. So the way we do it is we have our training set, and from there we take a slice that is then used for validation. This is a separate set.
Any questions? Thank you.